All right, everyone, welcome to GIA Knowledge Sessions, a series of talks and seminars about gemology fueled by our decades of research. At GIA, we consider ourselves so fortunate to study and learn, and it's our mission to share our discoveries with the world. I couldn't be more excited to kick things off today. My name is Natalie Jaden. I'm the Content Marketing Manager at GIA, and today I'm joined by Nathan Renfro, the Manager of Gem Identification, and Dr. Aaron Palke, the Senior Manager of Research. Just a few things before we kick off today's talk. Everyone attending is automatically muted. If you have a question, please submit it to the Q&A feature you'll see at the bottom of your screen, and feel free to ask questions as we go. There will be a Q&A session at the end where Dr. Palke and Nathan will be able to answer some of your questions. We will also send a recording of the session to you later today, and that message will also have a survey, and we would love to get your feedback. With that, I am going to pass it along to Dr. Aaron Palke.
So today we're going to talk to you guys about some microfeatures of gems. So if you've seen some of our previous talks, and especially Nathan's previous talks, we focus a lot on inclusions. What can inclusions tell us about a gemstone, whether or not it's been treated, what its geographic origin might be, but there's a lot more to it than that. I think there's also an avenue for us as scientists to use gemstones and their inclusions as a way of understanding Earth processes and the geological evolution of the Earth. So with that, I'm going to turn it over to Nathan. I think Nathan can describe a little bit about what inclusions are and how we use them in our work.
Thanks, Aaron. So what are inclusions and why are they important? That's really one of the main questions that geologists deal with. And inclusions are really any kind of optically observable irregularity in a gem material which can be used to give you information about the geologic conditions or even the formation conditions in the case of synthetic stones in which that gem material formed. The durable nature and the high transparency that you have in gemstones allow gems to really act like little time capsules. So any kinds of material that are collected within that gem act like little samples of the growth environment that gem formed in. And so it allows us to preserve that sample and examine it after formation, in places where we wouldn't normally be able to explore. So gems that form deep in the earth, we can't really visit those places because of the extreme conditions they form in. But gem minerals act like a way we can access that environment at a condition where we can examine in the laboratory. A few inclusion-related gemological books of importance here I wanted to bring up. So inclusions have been studied outside of gemology for quite a long time, but inclusions related to gemology, I would say one of the pioneers for that would be Edward Gublin. And his 1953 book is Inclusions as a Means of Gemstone Identification, basically chronicles several inclusions and what those inclusions mean. And so as a gemologist, when you have a microscope, if you can identify what the inclusion is, then you can unravel some of the story of that particular gem and gather information. And so the limitation is really your ability to recognize what the inclusion is in order to make that determination. And so the more experience you have and the more reference material you have available, the more powerful your microscope becomes. Later on, Gublin partnered with John Cuevla to produce the Photo Atlas series, which is a 3-volume set of inclusions in gems, which is really sort of the inclusion Bible in gemology. And so if there's any sorts of inclusions that you may encounter in your stone, there's a good chance that you'll be able to find a similar example in one of these 3 books to help you understand and identify what kinds of inclusions you see. John also later wrote a book called The Microworld of Diamonds. So it's specifically diamond related, which will help give you a better understanding on the types of things that you might encounter in diamonds.
And this is kind of one example I wanted to highlight. And I think it's kind of a really cool example. So as Nathan mentioned, a lot of what we know about inclusions in gemstones comes from some work in kind of the 20th century, when probably the optics of microscopes were getting better. We had pioneers like John Cuevla who taught us how to really master control of light in order to highlight inclusions a certain way and get the best photomicrographs possible. But I think it goes a little deeper than that. And I think the use of inclusions has been historically important as well in our scientific evolution. And I think one of the earliest examples of this, and I would say that amber is one of the earliest gemstones, if not the first gemstone where humans used inclusions to scientifically understand the history of gemstones from a geological perspective. And this goes back, the best example of this, I think, is Pliny the Elder, who was a Roman scholar, and he published his series of books called Natural History in AD 77. And he covered a series of topics from mining and agriculture and all kinds of different natural history topics. But one of his sections was devoted to gemstones. And in that section, he describes amber, and he describes the formation conditions of amber. And he used multiple lines of evidence to realize essentially that amber was fossilized tree sap. You know, one thing he noticed was when you rub certain pieces of amber with the cloth, you might evoke a kind of piney scent, which suggests that the amber came from a tree. But also he looked at these inclusions. He looked at the bugs and the insects that were occurring in the amber, and he realized, well, hey, those were insects that were sitting around when the tree sap started to flow, and they got captured in this tree sap and were fossilized along with the tree sap in the amber. And so really it's one of the first examples, you know, more than 2000 or about 2000 years ago, when humans were using inclusions in gemstones to understand the geological evolution of the earth. And I just think it's a really cool example.
And just like the insects tell the story of the amber, in a similar way, we use the inclusions in gemstones to tell the story of the gems that contain those inclusions. So we'll start out by looking at a few examples of solid inclusions in gems. And so our first example here is a ruby in its host rock. And so rubies from places like Burma form in marble, which is a metamorphosed calcite-rich rock. And so since the rock's primarily composed of calcite, when that ruby crystal is growing, it incorporates calcite inclusions to get trapped inside the stone during growth. And so when you look at a ruby and you find these calcite crystals, that tells you conclusively that the stone formed in an environment that was in a marble. And so you can really get some information about the formation conditions. So that would eliminate sources like Thai rubies, for example, which don't form in a marble. And so you wouldn't get calcite inclusions in that kind of rock. And so this slide just shows you how the host rock is really representative of the inclusions, and the inclusions are representative of the host rock. And so once you cut a gemstone and you remove the host rock, you can still look at the inclusions and get a sense of the geologic environment based on the mineral suite and the assemblage of inclusions that you might see inside that stone. Another similar example is this spinel, also forming in a marble with a dolomite-filled negative crystal. Now, spinel, even though it forms in a marble, the type of marble, it's still a carbonate, but in order to produce spinel, you have to have magnesium. And so spinel is a magnesium aluminum oxide as opposed to ruby, which is just an aluminum oxide. And so if you have magnesium in the carbonate, which is a calcium magnesium carbonate is dolomite, then that's going to have the nutrient material which will be able to produce spinel as opposed to ruby, which would generally occur in sort of a magnesium deficient environment. So just more of a pure calcium carbonate. So when you get inclusions incorporated into spinel that are carbonates, you might have these negative crystals that are filled with, that captures some of that host rock or the growth fluid. And so solid inclusions might be dolomite, and you might also have a fluid component like you see in this negative crystal. Similar things can be applied for emeralds. So this is an example of a schist-hosted emerald. So in emeralds, we really have two major types of growth mechanisms, and one is schist hosting. So you have these emeralds form in this biotite schist from regional metamorphism, where you have a contact zone with some sort of high heat volcanic activity, and so since all this biotite surrounding the emeralds during growth, when bits of foreign material get trapped in the emerald, the available mineral that's available to be trapped is biotite. So in these emeralds, especially from like Russia, Brazil, and Ethiopia, one of the dominant solid mineral inclusions that you're going to find is biotite. And if you're looking at a hydrothermal emerald, you're not going to see these types of minerals because they just weren't present during growth in order to be captured by the growing emerald. So here, in contrast to the schist-hosted emerald, we have metamorphic hydrothermal emeralds. And so these emeralds form in hydrothermal or hot water types of environments due to metamorphic activity. And in the case of this stone, you have a Colombian emerald, and the host material is this calcite rock, and you also have a lot of pyrite grains, and these form in these organic shales. And so you have these veins that are filled with this calcite and pyrite suite. And so in Colombian emeralds, you often get these inclusions of calcite and pyrite because those are the minerals that were present while the emerald was growing. And so that's what was available at the time for an inclusion to be incorporated into the stone. One of our staff members, Terry Ottaway, the museum curator, back in, I think it was 94, she did her master's work on the formation of emeralds from the Muzo deposit and was actually published in Nature. And so you can look this article up online, and she sort of goes over the formation conditions. And she used, for her work, she used information gathered from the fluid inclusions and from the pyrite grains to unravel the secrets and of how these emeralds formed in the Muzo deposit. And one of the key takeaways from that work was that in Colombian emeralds, they really have this sort of luminous quality, and that's because they have this reddish fluorescence. They have this reddish fluorescence because they're very low in iron. And one of the reasons why they're very low in iron is because of the formation of the pyrite, which has basically removed all the iron from the growth solution and sort of captured it, making it unavailable to be present in the growth of the emerald. So when you see these pyrite inclusions in Colombian emerald, those are the reasons why you have these really vibrantly glowing Colombian emeralds that have this sort of strong fluorescence, as opposed to the schist-hosted emeralds, which are generally much higher in iron because they have a lot more available iron to be incorporated into the actual structure of the emerald. Another small comparison here with our two main types of emeralds. So in the metamorphic hydrothermal types of emeralds, you incorporate lots of fluid inclusions and things like that. And in the schist-hosted emeralds, we have biotite grains like we mentioned here. And so there's another type of mineral inclusion we see in emeralds, and that's phenakite, but we only see the phenakite inclusions in synthetic emeralds. And phenakite is a mineral that basically occurs exclusively in a pegmatitic growth environment. And since we don't have emeralds that grow in a pegmatite, whenever you see phenakite, that is conclusive proof that you have a synthetic emerald, because that combination of inclusion to host doesn't exist in nature. So that's just another thing to think about. So if you see these kind of phenakite grains, that's proof for synthetic origin. We also see inclusions from sedimentary processes, which can also give us some information on the story of the gem. This is an agate from Brazil, and it has these metal oxides that have formed these kind of drip-like structures. And since we know that it's a chalcedony or an agate, and we know that those form in a sedimentary process, one of the rules for depositing sedimentary rocks is the rule of horizontal deposition. And that basically is where, for that, at the time that chalcedony was growing, it would be deposited in this layered type structure, and those layers would be perpendicular to the pole of gravity, forming this horizontal shape or this structure. And so what we can also see is that these metal oxides, as you would have impurities in these layers that would get incorporated as the fluid composition changed. So maybe the fluid became enriched in iron, and then you would have the iron deposited in this layer up here. Well, before this system solidified, gravity would basically pull more dense iron oxide minerals down through the chalcedony. And so we see that the influence of gravity on this more dense material. And so we can gather sort of the orientation that this agate formed in as it was present in the earth, based on the clues of knowing that the growth environment was a sedimentary environment, and that gravity would pull these more dense metal oxides in a sort of a downward direction. And so we can sort of unravel some clues about that stone there. A couple of other examples of agates formed in sedimentary processes. We also have this example of a dinosaur bone. And the sedimentary process is here preserve the dinosaur bone, which can then be used to gather geologic information about, the age of the rocks and the types of dinosaurs and other species that were present during fossilization. And this over here is another example of the metal oxides getting trapped into chalcedony. This is an iris agate, and it has these manganese oxide plumes that have been incorporated into the stone along the interface between this quartz and the chalcedony here.
All right, and for this next few examples, we're going to turn to garnets. And I wanted to take this part because I really love garnets. The first section we're going to talk about is Demantoid garnets. So Demantoid is the green variety of andradite garnet, which is a calcium iron silicate garnet. And there's kind of two main ways in which you can form Demantoid garnet, geologically speaking. The first is serpentinite hosted Demantoid, and the next one we'll talk about is skarn hosted Demantoid. So a serpentinite is a rock that originally started out as what we call a mafic rock, or an ultramafic rock, which is basically just a fancy way of saying a magnesium iron rich igneous rock, like a peridotite or something like that. And these rocks are formed of a lot of magnesium and iron silicates like olivine and pyroxenes. And what happens in the serpentinite is that you take that mafic or ultramafic rock and you expose it to hydrothermal fluids, so very hot fluids coursing through the Earth's crust. And those hydrothermal fluids will alter the mineralogical composition of that rock. So it'll take your olivines and your pyroxenes and it'll turn them into minerals called serpentine. And these serpentines are hydrated magnesium iron silicates. Now what you'll see on the photo on the left, this is a chunk of a andradite containing serpentinite from Russia, from the Poldnevaya mine. And I guess I wouldn't call this demantoid because the andradites are more brownish in this case, but this is the condition in which you would find those demantoid garnets. You see these nodules of kind of the garnets in there, these kind of roundish nodules, and those are surrounded by these sort of sinuous flowing serpentine minerals. And in this case, it's this fibrous serpentine mineral called chrysotile. And so on the next slide, we'll have some examples of that. When you look into the stone, so say you had a demantoid, you didn't know exactly where it came from or what the conditions were. If you looked at the inclusions, you could get a sense of whether or not this is a serpentinite hosted demantoid. So on the right, the photomicrograph on the right is this classic horsetail inclusion. And this is one of the better examples of it. These horsetail inclusions start out with this cluster of typically chromite centered at the center of the gemstone. Chromite's an iron chromium oxide. Again, a mineral you find a lot in peridotites and then in the hydrothermally altered serpentinites. And kind of emanating from that chromite inclusion are these fibrous minerals. And these fibrous minerals are a mineral called chrysotile, which is one of these serpentine minerals. And so it's what's causing that wavy nature of those serpentine minerals that we find in the ground. And so this kind of speaks to the geological origin of these demantoids, of course. If you saw this, you knew you were just looking at a serpentinite hosted demantoid. On the left is a diopside inclusion in a Russian demantoid. And again, this would have been one of those original minerals in the peridotite, which just happened to survive the hydrothermal alteration to get trapped in the andradite garnet as it was growing. And on the next slide, we're going to contrast that with the skarn hosted demantoids. So a skarn is sort of similar to a serpentinite, and that is the product of hydrothermal alteration. In this case, though, the original rock would have been a limestone or a marble, so something really rich in calcium carbonate minerals, calcite. And what would have happened was there would have been necessarily a intrusion of an igneous rock nearby. And oftentimes a more granitic silica-rich igneous rock is needed for this. So what happens is the fluids coming off of that igneous intrusion are quite silica-rich. So you have these silica-rich hydrothermal fluids circulating in this calcium carbonate-rich rock, and you get this combination of calcium and silica. And in these skarns, you form a lot of these calcium silicate minerals. And so andradite garnet, of course, is a calcium silicate mineral. So this is a great place to form demantoid. And in the next slide, we'll show you some of the other types of inclusions you might see along with those in these conditions of skarn formation. So in a skarn, you might form a lot of wollastonite. So wollastonite is a calcium silicate mineral that's shown on the left in the photomicrograph, these blades of wollastonite stuck in this skarn hosted demantoid from Namibia. And on the right are some diopside clusters, these roundish clusters of diopside that we often find in the skarn-hosted demantoids, especially from Namibia and Madagascar. Diopside is a magnesium calcium silicate, and it's very frequently found in these skarns because it's a calcium silicate mineral. So again, using these inclusions, we can backtrack the origin of this garnet to its geological origin conditions. We have just one more example of garnets on the next slide. This is an example of a manganese-rich garnet, a spessartine. So spessartine is the manganese-rich end member of the garnet series. You often get these beautiful, rich, vivid orange colors and these amazing kind of Fanta type orange spessartine garnets. This specific inclusion is a manganese-rich amphibole, and it was documented, I think, originally in the photo atlas by John and Koivula and Gublin. I think they originally described it as tiradite, which is essentially the same thing here as gosite, but tiradite is since then been discredited as a mineral name by the International Mineralogical Association, and so the proper name is probably gosite, but basically it's this manganese-rich amphibole. And so I just kind of wanted to drive the point home that the geological conditions that form the gemstones also are responsible for the inclusions. So the inclusions aren't just these random bits of material sucked up in the gemstone, but their formation is intimately tied to the formation of the gemstone host. And so if you want to understand more about the gemstone host from a geological perspective, it's a natural thing to do to look at the inclusions, because the inclusions can give you extra clues about those geological formation conditions. I think I'll hand it back over to Nathan for the rest of our talk about solid inclusions then.
Okay, so here's just an example of anatase with rutile inside quartz. So anatase and rutile are what we call polymorphs. So they share the same chemistry, which is titanium dioxide, but they have a different crystal structure. And the reason why they have a different crystal structure is related to the conditions of formation. And so when you have anatase, which is the core crystal here that you see in the middle of all these images, so below 600 degrees Celsius, the preferred form of titanium dioxide is anatase. And so this quartz will be growing anatase. And then what you might have happen is a modification of the growth temperature. So once the growth temperature goes above the 600 degrees Celsius, then that titanium dioxide still wants to precipitate out of solution, but it's no longer preferred. The preferred form now becomes the polymorph of anatase, which is rutile. So then you have the rutile nucleating off of the anatase crystals. So the interface between the rutile and the anatase tells you that's the point of this growth system where you had a temperature change across that 600 degree barrier. Another example of how the host rock relates to the inclusions is that we see in tanzanite. So tanzanite forms in these graphitic schists. So you can see that as the miner is pulling this sort of unheated brown zoisite, which will be heated and then become a bluish color and become tanzanite, which gets its color from vanadium. And you see the color of his hands, which is, he's got all this graphite, which has stained his hand. And so these stones they form in these graphitic schists. And so it's not uncommon when you do have inclusions in tanzanite. Typically tanzanite as finished stones are pretty clean. The inclusions get cut away. But if you do have an included tanzanite, you're likely to see these black plated inclusions of graphite, which is directly a result of that's what was available to incorporate into the stone during growth. And the same thing is true for Tsavorite, which forms in basically the same environment. Both stones are colored from vanadium. And you commonly, when you do have inclusions in stones like this, it's not uncommon to have these black platelets of graphite, which are captured from the host rock. A couple of examples of very specific inclusions that have really useful diagnostic value. This is an example of a pyrochlore inclusion in a Cambodian sapphire. Now, by the very nature of it being a pyrochlore, that gives us a clue that this is a sapphire that formed in a basaltic environment. And we certainly get pyrochlore inclusions that form in basaltic sapphires from a rather wide variety of locations. You can get pyrochlores in stones from Australia, stones from Ethiopia, but when you see these vibrant red colored pyrochlores, those are unique to Cambodia. And so if you have an inclusion like this, you have this diagnostic value in the inclusion that tells you there was something unique about the geology that not only formed the pyrochlore, but formed these sort of ruby red pyrochlore crystals. And so there's really a unique set of conditions that led to this diagnostic value in the inclusions you see here. And we see a similar thing that occurs in Muzo emeralds. And so there's a rare earth carbonate mineral called parasite that forms these sort of yellowish brown elongate crystals. And whenever you see these incorporated in an emerald, that's diagnostic of Muzo origin. There's really not any other location that has these inclusions preserved in them. And so this is another case where you have very specific localized conditions that was able to produce this rare earth carbonate that could then be incorporated into the gemstone. So you have diagnostic proof of Colombian origin when you see these parasite inclusions here. On to some diamond inclusions. Diamond inclusions are interesting, and the formation conditions for diamonds can basically be split into two broad groups. It's a lot, you can't really pin down the geographic origin of diamonds because they form deep in the earth, but you have two main formation conditions for diamonds, and that's peridotite, which is down in the mantle. And then you have eclogitic, which is when you have these high pressure conditions in the upper mantle, typically from subduction zones. And those two conditions give us two very distinct sets of mineral assemblages. And so we can identify the type of growth condition the diamond formed in when some of these distinct minerals are present in a diamond. So our first example is this chromium pyrope garnet. This is sometimes referred to as a G10 garnet and can be used as an indicator mineral when they're looking for kimberlite pipes to try to identify a diamond-bearing kimberlite. But this is indicative of peridotitic origin. And then another example of peridotitic diamond is when you have these dark black grains of chromite. Sometimes you can get a little bit of a brownish color on the thin edges, but a lot of times when you see dark inclusions in diamond, they're commonly referred to as carbon spots or graphite, but they're not always carbon. You can certainly have these opaque black inclusions that are chromite, which tell us a little bit about the geologic conditions of the diamond. You also have chromium dioxide, which is again consistent with peridotitic origin. And these are particularly rare, so it's not something that you'll commonly see, but when you do see these bright green crystals, you really can't miss that. And it tells you about the conditions of formation. You also have norringite garnet, which is a rare type of garnet that's chromium rich, which is also indicative of peridotitic origin. And olivine. Olivine is probably one of the more common inclusions that you get with peridotitic diamonds. So peridotitic diamonds form in a peridotite, which the similarity in name is from perido, which is peridotite is largely composed of olivine. So that's why you have a lot of olivine inclusions. When you do see a colorless or very pale green crystal, there's a good chance that it could be an olivine. This is a bit of a strange olivine inclusion. This one was blue, and it kind of tells us a little bit of a different story. It's a rather unique inclusion, and it indicates that the diamond may have formed at a much deeper depth than we would normally expect. And so if you want to read more about the work based on this inclusion, you can see the paper by Alan Bassett and Elise, or Bill Bassett and Elise Scalwald on the cation disorder caused by olivine ringwoodite phase transition. So you can pop that in Google and find more information on that. And then we also have some eclogitic examples. And so the eclogites are composed largely of a clinopyroxene mineral called omphacite. And then you also have garnets, which are almandine pyrope garnets. And so those are two of the major minerals that you get in eclogites. And so for eclogitic diamonds, those are probably the two most common inclusions that you'll observe. And it's not that uncommon to have them form together when they are present. So oftentimes if you see one, there's a good chance that you might see the other together. Another example of an eclogitic inclusion is kyanite. This particular stone was really remarkable. It's about a 2 carat, a little over 2 carat diamond. I had this relatively large inclusion of kyanite. This inclusion was about 1 millimeter across, which for a colored mineral inclusion in diamond is quite large. But that mineral kyanite would be consistent with the suite of minerals that we would expect in the eclogite. Same for corundum. This is another exceedingly rare mineral inclusion in diamond, but is one that that has been documented before. So we do have a blue sapphire inclusion. Rubies have also been documented. So, you know, basically chromium colored corundum, but in such small sizes, they may be very pale pink or may be red, depending on the amount of chromium present. We also had one of our GIA researchers, Evan Smith. He did quite a bit of work to using inclusions to reveal some more information about a different category of diamonds that he's designated as clipper diamonds, which is cullinan-like inclusion pore, partially resorbed diamonds that form in this sort of super deep environment. So if you'd like to read a bit more about Evan's work on the inclusions related to those diamonds, be sure to check out the winter 2017 issue G&G on the GIA website. And next up, we're going to talk a little bit about fluid inclusions.
All right, and I want to start off to talk about fluid inclusions, sort of strangely enough, with some inclusions that are actually not fluid anymore. So I think you understand a little bit more of this as we go, but essentially what I mean by that is inclusions that were trapped in the gemstones initially as a fluid, but since have either crystallized or quenched to a sort of a glassy solid state. They've basically frozen since they were included as a fluid. And the first example I want to talk about, and I want to go into a little bit of a depth with some of these examples, is the Yogo sapphire. So Yogo sapphires are found in Montana, in central Montana. They're the only primary deposit of sapphires in Montana. They're found in this volcanic dike. So this volcanic thin wall of rock, vertical wall of rock, and the volcanic rock, you'll see an example of that on the left. It's a rock called a lamprifier. And a lamprifier is sort of like a kimberlite, which brings up the diamonds from deep within the earth. So this lamprifier, this volcanic rock, also brought up these Yogo sapphires. And you can see a little blue sapphire right there in the middle of that rock. It's sort of a rare example of a sapphire in the host lamprifier. Now, one of the other features you'll see in that black lamprifier are these sort of white blobs. And those white blobs, Nathan, if you advance one slide, you see those white blobs shown here. And what we can also do with this stone, this rock, what geologists often do is we take these rocks and we grind them down into very thin sections. So you might have heard about thin section microscopy, where you take a rock and you grind it to about 35 microns thick. And if you grind it that thin, you can actually start to see through most of the minerals in most rocks we look at. And this helps us to identify different minerals in the rocks and to identify their orientations and their relative orientations with each other to try to understand how those rocks formed. And so what this is showing is that those white globs in the lamprifier that host the Yoga sapphires, you can also see these in thin section. And that's shown on the right in that photomicrograph. Now, if you go to the next slide, we can use a different technique as well called cross-polarized light in this with these thin sections. And this helps us to identify some of these minerals a little more readily. So what you saw is some of those white minerals turn black in that blob. That's a mineral called analcime, which is a sodium aluminum silicate mineral. Some of those white minerals turn this sort of pastel, colorful, these pastel colors. These are interference colors. And these specific range of colors sort of indicate the mineral calcite, which is a calcium carbonate mineral. And what we noticed further was that as we start looking at the Yoga sapphires, and yeah, so we can go to the next slide. The Yoga sapphires also have very similar inclusions to these white blobs we see in the lamprifier, in the rock. In the rock and the lamprifier, these are called leucocratic ocelli, which basically just means white colored blobs. In the Yoga sapphires, though, they have a little more form to them. They have a little more of a observable shape or geometric shape to them. They actually kind of have this, what we would say, negative crystal shape. These inclusions are composed of both analcime and calcite, just like those blobs in the lamprifier. But they also have their morphology imposed upon them by the host corundum. So if you look at this, the geometry of that inclusion on the left, it has that kind of trigonal geometry that you expect for a sapphire crystal. Now, taken together with the fact that it's kind of a heterogeneous inclusion, it has both analcime and calcite, this sort of suggests that it was not included as a solid. It suggests that it was included as a liquid. And in this case, this liquid would have been a carbonatite melt. So a carbonatite melt or a carbonatite magma is a magma that's composed dominantly of carbonate minerals. So calcite, there's some sodium and potassium carbonate minerals you can have in there as well. These are sort of rare magmas in the earth, but it sort of suggests that when this Yoga sapphire was growing, there was this carbonatite melt alongside with it. And this carbonatite melt in some way was interacting with the sapphire as it was growing. And it was somehow related to the growth of this sapphire. In the next slide, I'll show kind of an example of what a carbonatite melt is. So it's sort of a weird magma. Most magmas in the earth are silicate magmas. So the dominant component in most magmas is silicon dioxide. We form a lot of ordinary silicate minerals like diopside and olivines and quartzes and feldspars. In a carbonatite magma, you're not going to see so much of those. And actually, I think there's only kind of one known example of active carbonatite volcanism in the earth. And that's at this place in Tanzania called Old Doinyo Lingai. And I may have mispronounced that, but it's this only carbonatite volcano we know in the world. It's a sodium and potassium carbonate rich volcano. And so essentially if you wanted an analog for this, it's a simplification, but it's sort of like a big baking soda volcano in that it's a sodium and carbonate dominant volcano. And when it comes out, it's often black. The lava is black because it's not hot enough. It doesn't take very much heat to melt these carbonates. And so it's not hot enough to be that glowing red lava that you see in Hawaii and other places like that. And so it's just kind of interesting that you see these carbonatite melt inclusions also in these Yoga sapphires. However, on the next slide, we're going to show some completely different magma inclusions as well. So this, what I'm showing here are some glassy silicate melt inclusions. That's shown pretty easily on the photomicrograph on the left. You have this negative crystal shape. You have that little gaseous bubble within the glassy melt inclusion. And then on the right, it's a little harder to see. There's a lot of stuff going on in the photomicrograph on the right. There are some feldspar inclusions, some rutile inclusions, but also tucked behind one of those feldspar inclusions is another glassy melt inclusion. And so these are glassy melt inclusions, which indicates that they're not a carbonatite, but they're a silicate melt inclusion. So we have this entirely different type of magma that got trapped in these Yoga sapphires, as well as that carbonatite magma. And if we go to the next slide, we'll kind of put this all together and tell this really complex, interesting, and unique story about the Yoga sapphires based on observations of their inclusions. So we have carbonatite melts, we have silicate melts, and we have an entirely different silicate melt, the lamprifier. And all of these magmas were present and in some way interacting with each other, leading to the formation of these Yoga sapphires. And so it's it's kind of a really neat story how we can kind of get a little more information about how these Yoga sapphires formed by looking at their inclusions. And so in the next slide, we're going to go into another story. Oh yeah, sorry, I meant to plug our article as well. So Nathan and I published an article on the gemological characterization of the Yoga sapphires in the summer 2018 issue of Gems and Gemology, along with our colleague Dick Berg from the Montana Bureau of Mines and Geology. And we go into the gemology of the stones, we go into the history of the mine, which is really an interesting story. And we go into some of the geology and the other aspects of these Yoga sapphires. So if you want to learn more about this kind of unique gemological story, be sure to go check that out on the GIA website. So the next story is about the other Montana sapphires. And, Nathan and I really like Montana sapphires, so we often talk a lot about these stones. But they're kind of very unique and they have this really interesting story. So I'm also continuing this story about fluid inclusions, which are not fluid anymore. So if you look at this photo micrograph, we have two inclusions in the center of the photo, the kind of grayish pieces in the middle of that photo. Obviously, the more interesting part of the photo are those bright interference colors that you see, and that's produced by these two inclusions kind of rupturing out into the host corundum. And these were melt inclusions that ruptured out into the host corundum and created this sort of thin film interference that you can see when you get a fiber optic light shining on that, that decrepitation halo at just the right angle. Now, on the next slide, though, you'll see kind of a better example of what these melt inclusions actually are. And what you might see, that inclusion there in the middle, it sort of looks like what you would see for a fluid inclusion. And Nathan's going to show us some more fluid inclusions later, but you might expect that to be just kind of like an aqueous, kind of a water-rich fluid inclusion. However, if you go to the next slide, what we see with this is actually one of those inclusions that I sliced into. So I put that on the polishing wheel and I ground down very carefully until I just exposed that fluid inclusion at the surface. Now, what you would expect if that was an aqueous inclusion, you'd expect that fluid to leak away. But obviously that fluid hasn't gone anywhere. So what that indicates is that this fluid is not really a fluid anymore, but it's a glass. So this would have been originally a silicate melt that was trapped in the sapphire as it was growing as a fluid. And then as the sapphire cooled down, you quenched that silicate melt into a glass. And now when you cut into it, obviously that glass can't flow anywhere. But this is really a good thing for us if we're trying to understand the history of the geological history of the Montana sapphires. And when I say Montana sapphires, these are sapphires from the secondary deposits like Rock Creek and Missouri River, which are sort of distinct from the Yoga sapphires. But one thing to note as well, though, is that when gemologists see these types of inclusions, we often call them melted crystals. And there's a reason for that, which is that when you heat treat a sapphire at really high temperatures, if you have solid inclusions in there, the solid inclusions often will actually melt during this artificial heat treatment. And they'll melt and they'll turn into a glass oftentimes, and they'll look very similar to these types of inclusions. However, I would make the case that these inclusions in the secondary Montana sapphires are not melted crystals. These are actually blebs of magma that were present when the sapphire was growing. And on the next slide, I'll kind of give an example of that. So what we did in some of our early work on this is we took a bunch of these melt inclusions in the secondary Montana sapphires and polished them down to the surface so that we could put them on an instrument called an electron microprobe. Basically, an electron microprobe is a way of getting very fine scale chemical information at a very fine scale at like a micron level. And so we could take these inclusions and measure their chemical compositions on the electron microprobe. What you see on the right is a scanning electron microscope image of one of these melt inclusions that was polished at the surface. You see that contraction bubble, and you see the glass with the surrounding corundum host. And that's kind of what it looks like when you're measuring these compositions. On the left is a diagram that geologists often use in order to classify different types of volcanic rocks. So it's called the total alkali versus silica diagram, where you plot silica concentrations versus sodium plus potassium concentrations in these melts. And so what we found was one of the reasons we know these are not melted crystals is that the compositions of these melts is so dissimilar. It doesn't match any known mineral that it could have been melted to produce those inclusions. The only thing it really matches is known compositions of known volcanic rocks, like dacites and trachytes and rhyolites and andesites. And so this was one piece of evidence we used to prove that these are actually magma inclusions that represent the original magma that was present when these sapphires were growing. And so on the next slide, I'm going to wrap this up and then hand it over to Nathan with one more example of solid fluid inclusions. And so in this case, these are some sulfide inclusions. In some cases, not every case, but sulfide inclusions were probably trapped in their gem host originally as liquids. This is another example from Montana. So these are some sulfide inclusions. You see them, they have this sort of geometric shape that indicates that they might be negative crystals. They also have this decrepitation halo around them where the sulfide inclusion kind of burst out into the corundum host and filled that fracture with this black material. You can identify these pretty readily if you have a fiber optic light. These sulfides have a high refractive index generally, so the sulfide inclusions tend to have, they tend to be very shiny. They have a high luster when you get a fiber optic light shining off of them. And on the next slide is an example that we found in a faceted Montana sapphire that just happened to have one of these sulfide inclusions polished off at the surface. So this gave us a really good opportunity to go and study that inclusion to try to understand how it might have formed. And so what we did here was we put it on a scanning electron microscope, which is sort of similar to the electron microprobe I talked about earlier. It's another way that you can get very fine scale, micro scale chemical information about inclusions if you have them polished at the surface. And so what you see here is that inclusion you can also map out the different elements in an inclusion if you put it on the SEM. And so we're mapping out the sulfur, copper, and iron concentrations of that inclusion. And what you notice, especially with the copper and the iron, is that there are different heterogeneous distributions of those copper and iron in this inclusion. There are spaces where the copper is very concentrated, and there are parts where the iron is very concentrated. So what this indicates is that this is a mineralogically heterogeneous and chemically heterogeneous inclusion. Just like that carbonate melt inclusion that we talked about before, when you see these different heterogeneous inclusions, it often suggests that that was originally a liquid or a melt, that when it was trapped, it was liquid and homogeneous, and then as it cooled, it slowly cooled into different types of sulfide minerals at different parts of the inclusion. So this entirely suggested that these sulfide inclusions were trapped initially as melts. And we'll go to the next slide to go over one more example of that. This is some sulfide inclusions in Mozambican rubies. And again, one thing to notice, just looking in the microscope, these inclusions have these geometric shapes to them, right? And especially on the photomicrograph on the right, you can see this geometric pattern, and you can see the two sulfide inclusions have the same orientation, which suggests that their morphology, their shape was constrained by the corundum host. So they didn't form the shape of the minerals composing the inclusion, but they formed the shape of the corundum host itself. You'll also notice there's sort of a heterogeneous nature of the inclusions. You can see different phases already just using the microscope in those specific inclusions. And again, the inclusion on the left, another sulfide inclusion, this one has that decrepitation halo a little bit. It's also got that geometric pattern, and you can kind of see how it's aligned itself with the kind of faint fuzzy silk that you see in the background. Now on the next slide, I want to go over some work that our colleague Wim Vertriest from the Bangkok lab did. So he took several of these inclusions in the Mozambique rubies. He polished them down to the surface and put them on a scanning electron microscope again to map out their chemistry and see what was going on with these inclusions. And what you see here is these bright patches and these dark patches in these inclusions when you put them on the SEM. And these are indicating different chemical compositions in these sulfide inclusions in the rubies. And so again, just like with the Montana sapphires, when we saw these heterogeneous sulfide inclusions, this indicated that these were inclusions originally trapped as a melt, and that a homogeneous melt that then cooled down. And when it cooled, it precipitated these different minerals at different times, forming these heterogeneous compositions. And if you're interested in reading more about this, to the next slide, Wim recently published this work along with some work on the Mogok rubies, sulfide inclusions in Mogok rubies and Mozambique rubies. It was recently published in the journal Minerals, which is an open access journal. So if you want to go in there, Minerals 2020, you can go in and find this article and read more about Wim's work and get more of the technical details. If you need that link, feel free to reach out and we can provide that. So with that, I'm going to hand it back over to Nathan, I think, to talk about some actual fluid inclusions.
All right. So I just want to, again, kind of carry on with that theme that Aaron was talking about, where we have this sort of concept of homogeneous entrapment. So you have a liquid that was captured in a stone, and at the time it was captured, it was mixed thoroughly and basically homogeneous or the same composition throughout. And it's homogeneous while it's at this sort of growth conditions that it was trapped at. But then as the stone cooled down, you have this separation into different phases, or this sort of unmixing. And that's where you get fluid inclusions like the ones in this quartz. And so what we have here is a fracture in the quartz that happened during, while the quartz was still in the growth environment. And that fracture allowed fluid or nutrient solution from the growth environment to enter that fracture. And then the fluid helped to repair that fracture. And in doing so, it created all these little negative crystals. And each of those little negative crystals trapped a homogeneous fluid component from the growth solution. But then as the stone cooled down, that homogeneous fluid unmixed into its different components. So as the temperature decreased, the fluid could no longer dissolve whatever the solute was that was contained in the liquid. And so you have this unmixing effect. So this photo was taken using a technique called Reinberg illumination, just to provide a little extra contrast, but otherwise this is in a rock crystal quartz. And so what you'll see is that in each of these little fluid inclusions, there's the same ratio of the three major components, which is a solid crystal, which are these little salt crystals, these little cubic daughter crystals that you see. There's a gas bubble, and then there's the liquid that surrounds it. And so when you have all these fluid inclusions side by side, and you see this exact same ratio of solid, liquid, and gas, that gives you a clue that the only way for this to have been incorporated in this fashion was for the liquid to have been homogeneous at the time that it was trapped inside the quartz. And so with this quartz, because we only have one daughter crystal, which is the salt crystal, that tells us this was sort of a simple fluid. There wasn't a whole lot of excess chemistry or anything going on. But we also have similar examples in fluorite. So again, we have lots of fluid inclusions here, and we have a rather large one, and we have this blocky salt crystal, gas bubble, and then the fluid filling in the leftover space. And then if you look carefully in all these other little tiny fluid inclusions, you have this sort of same approximate ratio of gas, solid, and liquid. And so the same thing applies here, where you have this concept of this homogeneous entrapment, which trapped a thoroughly mixed homogeneous fluid. And then as the temperature conditions changed, and the temperature decreased, you have this unmixing of the fluid into its component parts. Now here's another example of fluid inclusions that were trapped in the same way, but the thing that's most dramatically different is you have, this multitude of daughter crystals. And so this is using plane polarized light, and so you can help see some of the separate solid phases here by the different colors. But the same basic components are still there, where you have each one has a gas bubble, a small liquid fraction, and then tons and tons of daughter crystals. And so in contrast to the quartz we saw before, this barrel from a pegmatite was clearly formed in a very complex fluid environment. And so if we were to heat this stone back up, we could dissolve this back into homogeneous mixture and see and it would represent the chemistry of the growth environment at the time this barrel formed. Here's a closer example showing one of these fluid inclusions with this whole multitude of daughter crystals. I've not tried to count all these, but you can imagine there's probably more than 20 daughter crystals. And then here's the gas phase, and then the liquid phase surrounding the gas, and then everything else here that has a little bit of color to it. Those are birefringent solid daughter crystals, which formed as a result of the cooling fluid or the unmixing. This is another interesting example of a fluid inclusion in a sapphire. And Sapphires from metamorphic environments, they form in these sort of silica poor environments, and so you don't get all those silicate minerals that you might have seen in the previous example. But the type of fluid that's present is carbon dioxide, and the carbon dioxide is trapped in the sapphire high pressure and temperature, and so you actually can get liquid carbon dioxide, just depending on the temperature that you observe the stone at. And carbon dioxide does this interesting thing where it actually will become a liquid at these pressure conditions at temperatures of around 31 degrees C. And so if you go above 31 degrees C, then the carbon dioxide will turn into this sort of vapor phase. Below that, you get this sort of liquid phase, and you get all these bubbles of carbon dioxide gas and then liquid carbon dioxide in between. And also, it's interesting that all of these negative crystals contain this graphite crystal. And so in a similar way to this unmixing, it appears as though that the graphite has unmixed from the carbon dioxide fluid, or that the carbon dioxide fluid had dissolved enough excess carbon to allow carbon or a graphite crystal to grow out of this solution here upon cooling. And so this is one of the most interesting carbon dioxide inclusions that I've encountered, and I've got a little video to show why. And so this is in the microscope, we can gently heat the stone and cool the stone down and watch this stone in real time and see the behavior of the carbon dioxide. And so here's cooling the stone down, and so the carbon dioxide is going into its liquid phase. And then after we get it into the liquid phase, so the next step, I took a hot point and I began to heat the stone back up, and turning the carbon dioxide into its sort of vapor gas phase. And these types of inclusions, when you see them in sapphire, they have some highly diagnostic value for the gemologist, because when you see these types of inclusions and you can cool them down and resolve these bubbles, which confirms the presence of carbon dioxide, that tells you that the stone's not been heat treated. Because if you had heat treated the stone, the internal pressure would build up so high inside the sapphire that it would actually cause the sapphire to fracture and rupture, and the carbon dioxide would spill out. So whenever you see these inclusions intact and you can cool them down, even with a piece of ice, and you can observe the bubbles form in your microscope, that tells you have unheated sapphire. One small exception is the newer high pressure heated stones, which has actually shown that because the confining pressure from the heat treatment at pressure, it prevents the stone from rupturing. So you can preserve some of these carbon dioxide inclusions in high temperature, high pressure heated sapphire. And our last category, these aren't really inclusions, but we also wanted to talk a little bit about the surfaces that we observe in some gem minerals before they are polished into gemstones. So the first example, I'll let Aaron talk about here.
Yeah, so turning back to Yogos as usual, this is the surface of a Yogo sapphire, of a rough Yogo sapphire. And we use this kind of special technique called differential interference contrast imaging. And so what we do essentially is we illuminate the surface of the stone with polarized light, and then we pass it through a prism which separates it and creates these interference colors, which are determined based on the distance from the point in the surface to the observer. And so what this can do essentially, it's just a way of highlighting surface features and topography on the surface of stones with color. And so what you see in this photo, this is actual true color of what you see when you look through the oculars of the microscope. These are not false colored images. And what we see with this especially is on the surface of this Yogo sapphire, we see these little triangular depressions. And kind of what's going on here is that when these sapphires, the Yogo sapphires, were transported to the surface by this lamprifier, this volcanic rock, the sapphires were not in equilibrium with that magma. So they were actually being slowly dissolved away and eaten away by the magma as they were being transported to the surface. And then that only stopped once the lava cooled itself and quenched and solidified, which allowed those sapphires to be preserved, even though they were called xenocrysts in the magma. And so that's shown up really well with this differential interference contrast images, because it really highlights those little triangular depressions, which is the points essentially where the sapphire was being eaten away by the lamplifier, it was being dissolved away by the lamplifier. And I think there's another good example of that on the next slide. I think this was one of Nathan's photos, but it's showing essentially the same features, these triangular depressions. And so we kind of know that they are etch pits, essentially, because the geometry of those triangular features are constrained by the corundum crystal lattice, which is trigonal in nature. And so when that corundum crystal lattice is being eaten away, it often is constrained, the shape of those etch pits is often constrained by the crystallography of the corundum itself, giving you those triangular pits.
All right. Then we have another similar example. When we look at the surfaces of diamonds, we also get these triangular etch features on the octahedral faces. And diamonds are a metastable mineral. And so when they're growing deep in the earth, they're nice and happy. But then when they're brought to the surface, they no longer want to be diamond. They basically, carbon wants to be graphite or some other stable version of carbon. And so as these diamonds are transported to the surface, they start to dissolve away because of they're not in a stable environment anymore. And so as the surface gets etched away, you get dissolution. And what's interesting on this particular example is the dissolution occurs in these sort of these lines of trigons. And these linear structures tell us a little bit about this diamond. And what it tells us is that these lines represent where a twinning plane intersects the surface of that diamond crystal. And because you have a twinning plane here, you have these localized areas of high defect concentrations. And so in those areas where you have high defects, you have much greater solubility. So those areas dissolve much faster than the surrounding areas. And so the surface morphology that we see in the microscope here, it gives us clues to the internal structure in this particular diamond. So we also can judge which crystal face we're looking at based on these triangular features, which only occur on the octahedral faces. But anyways, just interesting to see some surface structures in minerals. So we don't always look at cut stones in the lab here. We often try to get clues from rough minerals as well. And that pretty much wraps up our talk. So I think we'll move on to the Q&A section now, and be glad to take some questions.
Great, Aaron, or Dr. Palke and Nathan, thanks so much. That was a great presentation. We've got quite a few questions. I'm first going to start off with a two-part question. So the first part is, what type of microscope allows us to see such inclusions so clearly? And part two, can we use these clearly seen inclusions to determine geographic origin with complete certainty?
Okay, that's a good question. So the type of microscope that we use here, so in the lab at our desk, we have basically a standard gemological microscope. So there's nothing really particularly unique about it. A lot of the photo micrographs that you see, we do have some research microscopes available that have a little bit higher magnification available, but it's really not that different than what you would see in your gemological microscope. You can see one behind me here. This is a Nikon SMZ 25, and it probably has double the magnification power of a standard gemological microscope. But it's really nice that it has the camera attached, and so it just makes documenting illusions easier. But as far as what you would see in the microscope, a standard gemological microscope would show you pretty much everything that we saw here today, with the exception of the differential interference contrast images, and those require a microscope with specialized hardware called a Nemarsky modified Wollaston prism. And so that's really more of a compound type microscope that would have higher magnifying power. And then the second part of the question, I think, was what kinds of inclusions can diagnose or geographic origin with certainty. So occasionally there are several examples where we get suites of inclusions that tell us with a very high amount of confidence that a stone is from a certain locality. Two of the examples in the talk were the bright red pyrocolor crystals in Cambodian sapphire. So when we see that, that's really kind of a slam dunk case of this is a Cambodian sapphire. Even though we do get pyrocolor crystals in other types of sapphires, it's the appearance of those specific pyrocolor crystals that tell us with a high degree of confidence that that's a Cambodian stone. The other example was the parasite in the Colombian emeralds. That's a pretty strong indicator that you have a Colombian emerald. Of course, you would, in the laboratory here, we'd also tend to back that up with our trace element chemistry database that we've put together through lots of time and effort with our field gemology program that's been, I think, going on about 12 years now. And so even though the inclusions are really useful, we rely also on our reference stones, our chemistry analysis, and other advanced testing when we're making a determination about country of origin.
Awesome. Okay, thank you so much. Our next question would be, would chrysotile be considered silk when you're looking at these inclusions?
So the chrysotile we see in the demantoids and the serpentinite demantoids, you know, I think I probably would not consider it silk, and silk is sort of one of those maybe somewhat poorly defined terms anyway. Generally, when we refer to silk, it's the oriented, often rutile, but sometimes other types of inclusions. The oriented inclusions in sapphires often, although I think some other cases have been described as silk in other stones. But I think generally silk has that connotation of being oriented with relation to the host structure. Whereas that chrysotile, as you can see in that photo we showed, it's just kind of all over the place. There's no kind of real preferred orientation of the chrysotile. It's just growing out from the stone as the stone's growing out. So I would probably err on the side of not defining that as silk for that reason.
Okay, great. So can you tell us that photo of the Carbonate volcano, where was that taken? I was wondering that as well.
Yeah, that's in Tanzania. There's one place where you can find carbonatite, active carbonatite volcanism. That's in Tanzania at a place called Oldoinyo Lengai.
Fantastic. Alrighty. So we had a question about the definition of the term decrepitation halo. Do you guys want to touch on that really quick?
Sure. Decrepitation halo just basically means when you have a inclusion and it has ruptured, the ruptured disk that is produced is the decrepitation halo that forms this sort of 360-degree crack around the inclusion.
Fantastic. Alrighty. So we have a question about quartz. Does quartz have petroleum inclusions?
It certainly can. There's a deposit in Pakistan that I think it's Balochistan, Pakistan, that's pretty well known for the petroleum inclusions in quartz. You can also get petroleum inclusions in quartz from China, and I think even Spain and a few other locations, but probably the most prominent is the material from Pakistan.
All right, this is a really interesting question right here, especially for iron inclusions. Is there any relation in its position to magnetic north at the time the gem was formed?
So if it's magnetite, then I think the answer is probably. So magnetite, generally when it forms at high temperatures and cools down, there's a temperature at which the magnetism gets trapped in, and it'll slightly align its magnetic moment with the Earth's magnetic poles. And that's, if you've ever seen those stripy magnetic maps of the Earth's seafloor, you know, they're making these magnetic maps of the seafloor using these magnetometers, and they're measuring magnetite in the ocean floor. So probably the same thing happens in a gemstone. I guess I've never really seen anybody try to measure that though. Yeah,
you could run into another situation where if you have sort of a protogenetic magnetite inclusion versus like an X-solved magnetite, where if you had an X solution phase of magnetite, you might have more influence on the crystal host over the magnetism of the Earth. But yeah, I'm not sure that anybody's done a study to resolve orientation of the magnetic field in the inclusions though.
All right. Well, I think that is going to wrap up our question and answer session. Thank you everyone for joining us. We had some fantastic questions. If you have any more, feel free to contact us on our social media platforms. Thank you so much to Dr. Palke and Nathan for today's discussion. And don't forget that we have a talk next week about with Judy Colbert and Dr. Palke for green gems, history, lore, and gemology.